my name is Bill Harrison. I'm a senior scientist with the Cybersecurity Research Group at Oak Ridge National Labs, and I'm going to present some work I did with my then grad student Tom Reynolds and colleague at University of Missouri, Rohit Chadha, and my colleague at the U.S. Naval Research Lab, Jerry Allwine. So what I'm going to first do in this talk is discuss my motivations for this work, and then I'll discuss the actual kind of technical details and some applications. So this work is about a notion of termination that's called strongly bounded termination. And it came about through work that we have been doing on a functional language high-level synthesis tool called ReWire. And so I'm going to explain the motivation, how that came about. So high-level synthesis, or HLS, what is that? The basic idea is that most hardware tool sets, that is commodity vendor hardware description languages like VHDL and Verilog, lack software engineering virtues. And this is a fairly well-recognized problem with those languages. And that is to say that they lack the kind of nice qualities of good software languages, like nice abstractions and modularity and comprehensibility and things like that. Also, formal methods is another interesting thing that we know a lot about for software and perhaps a little bit less for hardware, certainly at the HDL level. So what high-level synthesis is about is the basic idea is saying, look, we're going to take software languages or ideas and constructs from software languages, and we're going to use them for hardware design. So there are a lot of these software, or a lot of these HLS languages. Some are based on C, so there's one called Leg Up. The idea has been around for a long time that functional languages should be a basis for these kinds of HLS languages. So way back in 1984, Mary Sheeran did a lot of work on some basic functional language to hardware compilers. And there are currently a number of efforts on using functional languages as a basis for HLS. So you may have heard of Chisel, which is based in the Scala language, and then our own tool, ReWire, which is based in Haskell. So why do we like HLS, and what do these things have in common? Well, all these functional language HLS tools are embedded DSLs. That is to say, there are host languages like Scala or C or Haskell, and some subset of those host languages can get compiled to synthesizable say VHDL or Verilog. And that has the advantage that you have sort of all of the usual DSL kinds of advantages. You get to inherit good stuff from the host language, whether it's sort of syntactic things like its front end or type system, or perhaps the familiarity of programmers with the various kinds of abstractions that the languages offer. And those host languages typically have the software engineering virtues. Now, there are some disadvantages to this approach, particularly if you're interested in doing formal methods. So you might ask the question with an embedded DSL, where does the host language end and the DSL begin? Can you distinguish between the two? Is there a formal distinction between the two? So for example, is a particular C program a leg up program? Or a particular Scala program, is it a Chisel program? Or a particular Haskell program, is that a ReWire program? And I say this is mainly a problem for formal methods, because in formal methods we really care about precision. You need to know what a program is before you can prove properties of programs. And so we would like to be able to distinguish these things. Now, in this particular setting of high-level synthesis, what that kind of boils down to is saying, maybe there are some programs in the host language that I can't compile to the hardware description language or to its synthesizable subset. And why would that be? Well, if you think about Haskell, which I'm going to assume that you're familiar with Haskell, there are a lot of powerful features in Haskell that, say, involve, that the implementation of which involve, say, unbounded stack. So just think recursion, sort of unbridled recursion as it occurs in Haskell, requires effectively, conceptually, an unbounded stack, and hardware has this fixed memory subset or fixed storage footprint that can't accommodate that. So let's look a little closer at ReWire now and what it's about. Just quickly, ReWire is a subset of Haskell. There's a compiler that takes any ReWire program to synthesizable VHDL. And so that, has nice properties. So Haskell has good qualities. I don't think that I would have to argue those too much with this crowd, but functional languages functional languages are good. I don't think anybody will argue about that. And the way we look at ReWire, the difference between, say, ReWire and Chisel is that ReWire is designed primarily as a formal methods tool. So we're investigating not only how do we compile functional programs to hardware, but we also want to have a semantics for that language so that we can do things like prove properties of hardware as described in ReWire. Now, we note that ReWire is a proper subset of Haskell. That is to say, there are many, many Haskell programs that simply, regardless of ReWire's definition, that many Haskell programs that simply cannot be represented in hardware due to their unbounded memory requirements. And in ReWire, how the main limitation that we use to distinguish ReWire from Haskell is we limit recursion. And in particular, we limit recursion to co-recursion in a particular monad. And I'm going to show you an example of that. Other kinds of restrictions are, well, you can't have unbounded types. So things like a list that can grow to unbounded size. You can't have that in ReWire either, obviously. So if I'm going to give you an example, obviously I'm going to give you the Fibonacci, right? And so what Fibonacci is, if you look at this blob here, and again, this is just a quick overview. The idea of Fibonacci is of this code is that it says, look, you give me n and m. I take interactive input b, and if that bit is set to 1, I don't do anything. I stay in the same state. If it's set to 0, I do the next in the Fibonacci sequence. And this chunk of code will generate a little circuit for that does this kind of bounded Fibonacci. What RE is a monad of resumptions over state. And so if you're interested in that, we have lots of publications if you want to hear the details about what that is. But the basic idea is that computations in RE have a feel very similar to synchronous hardware. Or another way of thinking about it is that they're very close to Mealy machines. So recursion in ReWire is restricted to co-recursion over RE is the bottom line. So that means, for example, that if we have a pure function f from a to b, Notice B is not in the RE monad, that is to say. How do we, is there any form of recursion that we can use on that sort of pure function? Currently in ReWire, we just disallow any recursion on types of that form, but it would be nice to be able to extend it. So how do we even think about that? All that is done in the context of a formalized semantics and calc for ReWire that Tom Reynolds did as part of his PhD dissertation. And so we want some way, if we're going to talk about extensions, this is describing our thinking, our motivation for coming up with the bounded time lambda calculus. How do we go about that? Well, the main thing we have to think about are what are the possible ramifications for hardware realizability. Let me show you what I mean by that. Generally speaking, when a hardware designer thinks about hardware, he or she thinks about a Mealy machine. And what a Mealy machine is, I expect this is not new to you, but it's a thing that is clocked. So it happens over discrete clock ticks. And at every clock tick, it takes an input I and the current internal state S, and it produces a output O and a new value potentially in the storage. And this happens at every time click. You can think of that as sort of abstractly what's going on. Intuitively, you might think that what is happening is at each clock cycle, there's this pure function f from inputs and store to outputs and store that on each clock cycle is being executed. Now, if f is a Haskell program, it could be, what kind of recursion could we allow in there? Well, clearly it's going to have to terminate according to the semantics, our calc semantics for ReWire. But any old termination won't do, because from the point of view of hardware realizability, you need to know that any call to f will terminate within a fixed number of steps. And the reason for this is not a theorem. You have to think about how hardware synthesizers deal with this. The fact is if it doesn't have this kind of strongly bounded upper limit, then the synthesis tools like Xilinx's Vivado won't be able to determine a clock cycle for that circuit. And so it won't be synthesizable. Again, this isn't a formal statement. This is an informal argument, but to formalize it, you would have to have a formal notion of what Vivado or other synthesis tools would do, and good luck with that. So type-based approaches to termination are found frequently in the literature, and what the bounded time lambda calculus does is it formalizes the notion of strongly bounded termination, and it is a calc mechanization of that formalization. So there are a number of related works that have more expressive languages, but without mechanized proofs. So they are sort of paper and pencil languages rather than, say, a calc language. The basic idea that all of these things have is that they annotate types with numbers of steps. And so the idea is that if you know the number of steps that individual parts of a program take, then you can track its termination, basically. So for the bounded time lambda calculus, what we have to do is decorate. It's a simply typed lambda calculus, but we decorate the types with types and type constructors with these kinds of number of steps indexes. We did this and mechanized it in Coq and proved all the usual nice meta theory that one would want. So the presentation of the formal details in this talk are very brief. We do have the Coq development complete, freely available, and so see that or the paper for more details. Generally speaking, though, what it does, what our mechanization does, is what the other related work does. Is it basically says, look, we're going to annotate types by these kinds of indices, and then we can incorporate these indices within the type system for the language. Here I've showed the case rule. The basic point is that the indices from the sub-expressions end up determining the indices for the case, for the index for the case. The small step semantics for this language is completely unsurprising. So I just flash it up, or flash part of it up on the screen for your edification. If you want more details, you can see the paper. And then we were able to prove in Coq a number of the usual kinds of metatheoretic theorems that one would want. And again, I'm not going to go any further into this. There's not surprising material in there. We show a particular application of the bounded time lambda calculus to timing channel analysis, where what we do is we alter the type system so that primarily only on the case rule, we just replace the case rule where it has an extra hypothesis, basically saying that the time that t takes has to be equal to the time that u takes. And then we show some examples, also mechanized in Coq, and we prove timing channel freedom for this altered type system. So, in summary, what we've presented is the bounded time lambda calculus, its syntax, and semantics, and meta theory. All this is available. All of this mechanization is available in Coq. All the theorems, every formal statement we've made in the paper is proved in Coq. And the point of the BTC is to formalize strongly bounded termination, which, as we say, was motivated by hardware synthesis from functional programs. We also gave a nice case study in timing channel analysis, which is somewhat reminiscent of work by Johan Agat from 2000 in his paper Transforming Out Timing Leaks. So this work originated in a effort to formalize the semantics of the ReWire functional hardware description language and to formalize it in Coq. That is also available and described in detail in Tom's dissertation and in several recent publications. So the motivation here for us was just thinking about how we would go about extending ReWire's expressiveness, that is to say, how to include other notions of recursion, particularly for pure functions. There's a theoretical question, which you might think of, is there some way of identifying A-class or the class of hardware realizable functions, and say as a subset of Haskell, say, and can such a subset be identified by suitable type system? And we don't claim to have an answer to this, but this was also part of our discussions in coming up with this. So as BTC came about, because we were thinking about ReWire's formalized semantics, we expect to extend or integrate BTC or some descendant of BTC into a ReWire semantic mechanization, and we're doing a semantic specification of ReWire to kind of take advantage of all the lessons learned, and except we're going to do this in Agda, and this is largely complete, but look for that. That's kind of an upcoming attraction, or coming attraction. So thank you very much for listening to my talk.